Hello, Mr. Ryan. How are you today?
Yeah, maybe good.
Yesterday we talked about list factor combination. So
Yeah.
basically, we're trying to find out a list of factors that whose product is the n, right? For example, 12. The list of products is we can have is 2, 3, 2 or 2, 2, 3. These are considered as the same, right? Okay. So the algorithm we're using yesterday is backtracking, which is basically like recursive depth search with some optimization. So one optimization is that we don't want to continue with the duplication. For example, like 2, 2, 3 is the same as 2, 3, 2. The idea for this optimization is that we keep tracking of the last user factor. Okay, so for the next factor we're going to use, it has to be no less than the last user factor. Okay. Yeah. So look for this one. Yeah. Depth search n is the current integer, s is the last used factor, c is the current list of the factors. Right. And now we start with the s up to square root of n. We talk about this square root of n, right? For example, like if we want to find out if 100 is a prime number, so how do we do it usually? 100 is an even number. For example, like 121. If it's a prime number, how would you usually check if it's a prime number?
It's not a prime number. If it's
yeah.
in 1,000 times tables.
121. Okay. So how do?
Okay, I just remember my times table squares.
Yeah.
And I just remember 11 times 11 equals 100.
Okay, so but if it, for example, if you're not remembering those, for example, which timetable you start checking? 2 times table, 3 times table, 4
I
times
start
table.
checking the 3 times tables.
Yeah. 2 times table, we can easily rule out for the even numbers. Yeah, if it's not an even number, so we don't need to check 2, 4, 6, 8. It doesn't matter, right? Because it's not an even number, it certainly cannot be divided by 4, 6, 8. Am I right? It's not in those even numbers timetable. So we start with 3, 5, 7, 9, 11, right, etc. So the idea is we check these factors up to square root of n, right? For example, 100, we have 2 and corresponding, which is 50. We have 4 corresponding is 25. So look, we have a number which is less than square root of n, then sure we have another factor which is bigger than the square root of n, right? 4 times 25 equals 100. Yeah, it means that we also have another pair. 25 times 4 equals 100. Okay. So we are incrementally building the list of the factors c dot append I. Once we found out the I is a factor of n, right? So we can build an answer which is the I and n divided by I. So then we backtrack. We find a factor I, so the remaining factor would be n divided by I, and then the last user factor would be I, and the list we're passing in. So the idea of backtracking is that afterwards we need to restore the list. Okay. The other way we don't need to modify the C is that we pass a copy. So instead of C dot append I, so we just do this C. Yeah, and we put another one I and divided by I, and then C just plus I. Okay. Yeah, so we don't need to do this, right? Because we are passing a copy of it, so we don't need to restore it. Okay. So today we're going to talk about breadth search. Basically, it's quite similar than that, but we are just expanding our search tree level by level, in a level by level order. Okay, so I guess you must be very familiar with breadth search. So how do usually you implement a breadth search? Using what kind of data structure? Q. DQ, double NDQ. Okay.
Answer dot append, Q dot append, Q dot pop.
Pop left here. So we use the
right.
DQ, double NDQ, because we want to achieve the O1 constant, the most efficient way to do this operation in both sides of the queue. Pop left, append left. If you don't specify the directions, by default it means step to the right. Okay. If you want to pop from the left hand side, we have to put the left, pop left, append left. Okay. If we say append, it's on the right. If we say pop, it's from the right. Okay. So answer equals empty list. This is the answer we're building. So at the beginning, DQ we put the, because we are requiring 3 parameters. So the n, we're putting the n. We start with 2 because the smallest factor could be 2, right? The smallest factor is considered as up from 2 up to n, not including. Okay, this is the closed, and this is open. This is the same thing as factor bigger than 2 and smaller than n. Okay, and the list at the beginning is empty. This is empty. We are pushing a tuple, right? A tuple three elements. What's the difference between tuple and array list? Anybody?
Tuple looks different.
Tuple
Tuple is an
immutable. Immutable means that we can't change it once
and
we
a
have
list
it.
is mutable.
Mutable, well done. Okay. So wire queue. So this is the standard buffer search. We take it from the queue. We dequeue it. Yeah, we dequeue it. So the number.
Tomorrow I'm doing swimming. Oh yeah.
Okay. The last factor and the current list equal q dot pop 1. We are using the dequeue as a queue, so we need to q dot pop left. Easy. And then these will be the same. Therefore, we need to check. We need to check the next possible factor. Factor. So for I in range, we start with the last. We go up to num square root of n num. Yeah, square root of n. There are 3 ways of doing it. Right. Integer n multiple 0.5. We talk about this, or we can use the power function, or we use the sqrt function. Those are okay. Plus 1. If num divided by I remains 0, right? So it means that if I is a factor of num, answer the append. We push it. We find one solution, which is the current plus I and n divided by I, right? Once we have a factor I, we also have a corresponding n divided by I, and then we need to push the results, push the kit, q dot append n. Okay, this is the n divided by I. The last unit vector is I, and the list will be current. We make a copy. Wait, are you okay? Plus
yes.
I. Okay. We finishing with this. We can answer. This is the numbers, the I. Okay, numbers I. Right? Numbers divided by I. Okay, numbers divided by I. So I is a factor of num. So we push the result. We have a result with current. This is the current list of the factors, and plus I and num divided by I. Okay, and then with the next kit we're going to explore is, once we have found the factor I, the remaining is n divided by I. The next factor to be used should be no less than I, should be I or more. And then the list, yeah, we found the I, and then we append it. And we need to make a copy. Yeah, we can either use this list current or current, this is array slicing, or we use the copy.decopy. It's the same, okay. Decopy. Can anybody tell me what's deep copy?
Is a copy that deep?
Deep copy, what's deep copy?
It's basically copying.
Yeah. So what's the opposite of deep copy?
Shallow copy.
Yeah. So deep copy is copy everything. Yeah, you can treat it as copy everything. Shallow copy is more like an alias, right? Alias. So you just copy the name, right? Does it make sense this way?
Yeah.
Okay. For example, like array equals 1. B equals A. Is this shallow copy or deep copy?
Shallow copy.
Shallow copy. B points to A. So B and A is the same pointing to it. But if I say this is the deep copy, yeah, or we can use deep copy. Copy.decopy A. B equals copy. This is a package.decopy A. Right? This is the same. Or B equals list A. We convert into a list. So look, this one, and this one are all deep copy, right? But this one, B equals A, this is shallow copy. Okay? Okay, so today, what have you learned so far? What's the last? What's the thing you learned today? Come on.
About breadth search factor company.
Okay, so what's the problem and
The
how?
problem is we got a number.
A positive number, yes,
Yes.
integer n.
And we have to do all of the
We want to find out the
Factors.
list of factors. Yeah, the factors should be more than 2 and less than n, right? So if we given a 2, we don't find such vectors bigger than or equal than 2 and less than 2, right? There is no such thing. And any prime numbers, we need to return
emptiness.
empty list because we don't find such valid factors in this range between 2 and n, right? Not including n. Okay. So yesterday we talked about recursive depth search with some optimization, which is essentially is the backtracking. Yeah? Backtracking is the depth search with optimization. Right? Depth search, we travel the search path, search tree, as deep as we can, right? And then we backtrack if we can't find a solution. We don't keep continuing. We don't continue deeper if we found an obstacle. If we don't find a solution, okay? But for the breadth search, we travel the search tree level by level. And in order to do this, we use the DQ. We do this level by level, okay? Okay, that's it for today. Bye bye.
Bye bye.
Bye bye.